Hello all, welcome to the video series on signal integrity and power integrity by EFR Engineer. In the last video, we have seen that all the signal integrity problems can fall into three categories and they are timing, noise and EMI. In this video, we hear a lot of signal integrity noise problems like ringing, ground bounds, reflections, near end or far end crosstalk, etc. All these problems can be related to the electrical properties of interconnects and how they affect the digital signals. Looking at these problems, it feels like there are so many signal integrity issues and how one can take care of them. But if we pay closer attention, then all these signal integrity noise problems like ringing, ground bounds, etc. can be related to one of the four categories listed here, and they are signal quality of one net, crosstalk between two or more nets, the rail collapse in the power and ground distribution, and finally the electromagnetic interference and radiation from the entire system. So, if we can identify the problem and categorize it into any of these categories, then the solution becomes obvious. So, now let's focus on the signal quality of one net now. The signal quality on a single net depends as much on the physical features of that signal as on the return path. So, if we look at a particular signal net, it is obvious we should look at the return path as well. So the return path for a single net is very important. And the four aspects we need to keep in mind when seeing the signal quality of one net are impedance, rise time of the signal, the frequency dependent losses, and the attenuation of higher frequency components by the dielectric. Now let us see this impedance. So as the signal propagates down the interconnect, it always asks the question, what is the impedance I'm seeing? If the impedance seen by the signal is same, then the signal continues to be undistorted. If impedance changes, then the signal will reflect from that change and continue through the rest of the interconnect as undistorted. This impedance of a net changes if its cross-section or geometrical shape changes. We call the feature that changes this impedance as discontinuity. And some of the discontinuities that change the impedance are the line change width, layer change through a via, a gap in the return path, or end of a net, etc. The impedance discontinuities can rise from the cross section, topology of routed traces, or any added components. The most common discontinuity is what happens at the end of a trace, which is usually either a high impedance open at the receiver or a low impedance at the output driver. In order to have less discontinuities, we can have constant or controlled impedance traces or use rules that allow the topology to maintain constant impedance, or finally use strategically placed resistors to manipulate reflections and keep the received signals looking clean. And coming to the rise time, the impact on a signal from any discontinuity depends on the rise time of the signal as well. As rise time gets shorter, the magnitude of the distortion increases. This is why a discontinuity that was not a problem in 33 MHz design may be a problem in 100 MHz design. And there are two more aspects of signal quality associated with one net, and they are the frequency dependent losses in the line from the conductor and the attenuation of high frequency components by the dielectric. With all of these effects, the signal rise time increases as it propagates, because all these effects like impedance changes, rise time distortions, losses, attenuations, all these things impact the signal. So when the signal is impacted, the rise time increases as it propagates. When the rise time degradation approaches the period of a single bit, then the digital information will be distorted, and this phenomena we call as ISI. That's all on a signal quality of one net. and we will see the rest of these three in the coming videos. Stay tuned and thank you so much for watching. Subscribe to IFR Engineer.